HPC solution architect in Intel's data center sales group. So the plan for today is to try and stay away from the products a little bit and give you an update on some of the technologies that we're working on and investing in around the areas of what we would call technical computing, which would span HPC, AI, and analytics. So I won't dwell too long on these slides. We've kind of seen some similar ones from other presentations. It's really just talking to the fact that, if we'd had this presentation a year or two ago, we'd really be focusing on on HPC specifically, but really a recognition that over the last few years, the expectations from the industry and the capabilities that we need to deliver are broadening in their scope and in their breadth, and it's therefore beholden on us to start developing the technologies which support these new workloads and enable these new capabilities. Similarly, with new capabilities comes new user expectations. New groups are looking to access these systems, run new workloads. I think it was quite interesting yesterday with Mark's presentation looking at the different domains and disciplines that are looking to use these systems. And up there was humanities and social sciences. And I think it's probably quite unlikely that a couple of years ago that would have been called out specifically as a large user group. So as we get access to more data, to new systems, to new capabilities, we need to support these new methods of access and the new user groups that are coming and trying to make use of this technology. So I asked our marketing team for a very simple and concise slide which would give us a sort of an overview of what we were doing. So this is what came back. So I'm not going to go through everything on this slide because we don't really have time, but I'll touch on a few things. There was one thing before I start drilling down into a few of the sections. We hear a lot about the end of Moore's Law, and there was even a few comments about that in presentations yesterday. And I think, the packaging piece at the top I'm not going to drill into, but it's worth kind of calling out. You look at what Moore's Law is, I think we kind of, as the Moore's Law company, I kind of need to say something about this. And there's a lot of process technology improvements and also packaging improvements that we are working on around planar packaging, 2.5D, 3D stacking of chips. Moore's Law fundamentally is an economic argument in terms of delivering transistor density and delivering capability at a reducing cost. And things like change of materials, moving to 3D FinFET from planar transistors, changing the packaging, these all contribute to that Moore's Law. So I think, it reminded me, we get a presentation internally from a gentleman at Intel called Jim Keller, who is the head of our silicon engineering group. And he called out a quote when he was referencing the doomsayers, I guess, around this kind of area that, it's been predicted for quite a long time. If you talk to people in the industry, they don't seem quite so concerned. You talk to the cutting edge fabs, whether it's ourselves, Samsung, TSMC, they all seem to have a roadmap that runs out several generations for several years. So we keep plowing on, we keep politely smiling at the naysayers, and we continue. Right, so architecturally. So, obviously, the processor, the compute unit is kind of central to everything that we're doing. It's kind of a realization, I think, that currently there's not a one-size-fits-all approach. We've extended our portfolio of technologies. We've started to look at these in terms of 4 different areas: scalar, vector, matrix, and spatial. And depending on your priorities and what you're trying to achieve and what you're trying to deliver, if it's flexibility and running any workload on your platform, the CPU is still a kind of primary platform there. Once you start looking at energy efficiency or outright pure performance, you start moving along into things like our XE vector GPU technologies that we've disclosed recently, the Nirvana neural network processors, giving us a much more efficient and high performance compute unit for deep learning applications, or even things like FPGAs to give us the highest flops per watt. So there's an entire spectrum of technologies there. And then just to throw into the mix, there's also a lot of work going on around quantum and neuromorphic development as well. So we have chips in the lab today, quantum chips. We have quite a few white papers and things published around a chip we're working on called Tangle Lake, which is a 49-qubit chip, which we're working on with TU Delft in the Netherlands. And then the neuromorphic effort that we have a chip called Loihi, which again is basically trying to mimic the characteristics of a biological brain in silicon. So moving very much away from the kind of von Neumann model that we've kind of had for decades and decades, and looking at, well, actually, if we were starting this again and we wanted a chip that was going to be very efficient at the kind of operations that the brain executes, what would we do and how would we do that? So a lot of different areas trying to capture the requirements of all of those different workloads. Tying all of that together, making a CPU is great, but as we look out towards system level and cluster level, we've recently announced, and this is not something that's going to be a product imminently, but we have to kind of start the industry adoption of this. We recently announced an open standard and a consortium called the Compute Express Link, and this is focused on building a coherent interconnect between our CPUs and other sort of complementary devices within the system. So this is an open standard now. We've turned it over to the community. I think version 1.1 was published quite recently. Most of the large industry players are involved in this effort. You could probably guess the ones that aren't, but typically we're seeing good adoption and interest in this, and you can see this technology will come down the pipe and will intersect with our CPU and platform technology in the relatively near future. A little bit of a tangent in terms of sort of complementary technology here. The previous presentation talked a lot about Optane persistent memory, which was great because I don't have a lot of time to talk about it, but it really changes the way you think about how you move data within a system and what you do with that data. And as well as it just being storage local to a node that's very high latency, very low latency, very high capacity, we then are able to do things around DAOS. So this distributed asynchronous object store technology that we're working on requires a storage media like Optane to drive the levels of performance that it targets. So these things working in tandem will enable sort of exascale level file system access. What we're doing with DAOS effectively is, rather than considering access to your file system as something you do over a network to a remote file server, you basically overlay the DAOS file system across your compute nodes. So your point of access into the file system is local to the nodes. You can change the personality of a compute node into a DAOS server, and it becomes the egress-ingress point to your file system within the cluster. And then behind that, it leverages the NVMe stack and it leverages the Optane technology to provide very, very low latency and very, very high performance and high throughput file storage. So crucially, this technology, it's not a POSIX compliant file system, but what we are doing with DAOS is we are providing layers that sit on top, which enable either POSIX access or something else which is better suited to the workloads that you're working on. So from effectively groups of APIs or interfaces to the file system, whether you're doing database, whether you have a particular machine learning or deep learning workload that would benefit from a certain data structure access, sort of blob access into the file system, or whether you just need POSIX compliance, all of those things are possible, but it's basically a re-architected way of storing and accessing data at very, very large scale. Something just worth touching on with Optane, actually. So, a lot of people have been talking about its memory persistence. It's probably also worth pointing out that this is a technology which appears in NVMe connected SSDs as well as the persistent memory modules. It's a technology which, as well as being sort of cache line addressable and a persistent memory technology, it's also block addressable. So it really blurs the line in the system between what is system memory and what is storage, and it opens up a lot of different opportunities for how people choose to structure their workloads, move their data around, and access their data. I think I'm flying through this. So this is the kind of piece that wraps everything up, I guess. So, making hardware is great, the complementary hardware, the adjacencies, making sure that we have a system-level approach to this technology. But ultimately, performance tends to be extracted through software. I think there was a comment yesterday morning from EPCC that they had I believe it was potentially a machine learning workload running on a system, and through restructuring some algorithms and taking a look at what the code was doing, they ended up with something like a 48 or 50x speed up. And that wasn't a hardware change, or it wasn't anything fundamentally to do with a new product. It was purely taking a look at their application and making those changes. So over the last several decades, Intel has made some huge investments in our software development tools, whether it's vTune, Intel Advisor, our MPI libraries, making sure that you get the best return on investment off our hardware using our development tools. So we are a contributor to the OpenHPC initiative, and we put a lot of code back into that in terms of cluster management and cluster administration tools, power management tools, etc. Something which we announced recently, and which I think we're going to announce more details on around supercomputing, is an initiative that at the moment is currently called One API. Whether it continues to be called that, we'll find out at supercomputing, but effectively it is an effort to produce a common developer environment regardless of whether we're talking about the scalar vector matrix or spatial compute units that I mentioned at the very start. So it's based at its core around data parallel C++ programming language, although for the Fortran and C++ users out there, there is still full support around those programming environments as well, but it really is designed to maximize your capabilities on targeting different platforms from a single code base. So, we do a lot of work at the moment at the API and library level to make sure we get these optimizations, and we're trying to make that an end-to-end optimization so that regardless of the platform you choose, you get a consistent user experience and you get a high-performance experience as well. So this is something you'll hear a lot more over the next few months. I think we're going into a closed beta towards the end of this year, and I imagine there will be an open beta happening sometime in 2020 if it's something which, as a software developer, may be of interest to you, particularly as we see things like the Nirvana neural network processors, the XE GPUs coming to market, preparing for them, getting ready for them, but not having to redo your entire code base in order to target those platforms. This is something which we're actively working on in preparation for that. And I'll skip that slide because there's not enough time. So just to wrap up, this is the motivation, I guess, behind why we're developing in all of these different areas. Your productivity, the work that you do, it's not only about the system. It's no longer sufficient to just make a good CPU, right? We make microarchitectural enhancements to our CPUs. We introduce things like AVX512, so we double the number of flops per cycle compared to the old AVX2 specification. We introduce things like Intel DL Boost, so for VNNI instructions, which is our vector neural network instructions for inference. We collapse down the three most common convolution operations into a single operation, getting up to 3x speed up. So, we're constantly driving that development. But then you're looking at efficiency as we scale out, things like DEOS, re-architecting how we do data placement and data access, how we do scaling, whether that's at a hardware level, whether it's through our Intel MPI effort. And then finally, and arguably most importantly, it's then unlocking that performance through our software and developer tools, performance libraries, optimized deep learning frameworks, and the development tools that sit around that. And I think that brings us to the end. Thanks.